Okay, in this lesson, we're going to look at section 4.1, scatter diagrams and correlation, and we're going to look at a specific example. I think if you see an example of scatter diagrams and correlation, the learning objectives that you see described here will be a little more clear. So what I'm going to do is I'm going to do an example, and I'm going to make up some data, and from that data, we're going to create a scatter diagram. And then we're going to look to see how that data in the scatter diagram is correlated. So let's go to Excel. So if I've got a data set, what you see right over here, here's my data set. I went to 10 people, not really, but I went to 10 people and I said, hey, how much do you weigh and how tall are you? And so I have data for each of the 10 people. What I could do with that data is I could say, well, you know what? The people's weight is going to be my x-axis and people's height is going to be my y-axis. So I could take this data and I could graph it. Remember, this is the x-axis and this would be weight. And if you're saying, hey, why is weight on the x-axis? Just because I had to pick one. There's not a particular reason in this particular case. My y-axis is going to be height. And so if I look at Abe and I was going to plot where Abe was, I would come over here to 125 and I would go up to 63 and I would have this point right here. That point would describe Abe. So if I wanted to describe Bob, Bob weighs 138 pounds. So I'd go over to 138 and Bob is 64 inches tall. So that point right there would describe Bob. And so I could go down for each one of the points that I have here, and I could describe an X and a Y value for each one of those. Now, we could do this by putting specific points on a graph, all right, and it would be really ugly. Let's do that same process, but let's use Excel to do that. So if I want to graph this data in Excel, what I'm going to do is I'm going to select my data right here, and I'm going to select Insert, and I'm going to select Charts. And the type of chart I'm going to select is a scatter chart. So I select that chart. I'm going to slide it over here just so I have a little bit more room. So what I now have is I have a scatter chart. And what it's doing is it's relating the weight and height of these 10 individuals to each other in a graph. So if you look back at the learning objectives, that this is what is meant by a scatter diagram. We have a scatter diagram in this particular example. And we have a scatter diagram because we've put X and Y on each axis. So I'm going to go a little bit further and make this graph prettier. So I made this graph a little bit prettier by labeling the x-axis and saying, hey, that's weight in pounds, and the y-axis, that's height in inches. So I have this particular relationship here, and this is my scatter diagram between, in this case, height and weight. If you're looking at this data, you might be able to look at this data and say, you know what? It looks like, in general, as a person's weight goes up, it appears that their height goes up as well. Of course, I made up the data. But you can look at the graph here and you can say, you know what? I mean, you kind of see a trend here where when weight is going up, it appears that height is going up. How could we represent that relationship? Well, one way we could represent that relationship would be with a line. So I drew that line right there. Well, what if I drew this line right here and I said, hey, that line represents the relationship? You could probably say the red line looks better than the green line. So if I look at my lines, the red line is a whole lot better fit than that green line was. We'll get into more specific about what makes a line a best fit line, but it's easy enough to say if I've got a line that's somewhere else that doesn't match or fit the data as well as a line that's close to it. Now, in this particular relationship between weight and height have a positive correlation. That is, in general, as according to this data, as the weight goes up, as the values go this direction, the corresponding height of people also goes up. So from this data set, this data was set, and you can kind of see it here where I've named the worksheet down here. This data set is a positive correlation. I'm sure the very next thing that comes to your mind is, what does a negative correlation look like? And I've got a tab for that. So if we look at a negative correlation, again, I made up some a data set here, and we can call it the same set of people, and I have listed the people's weight and their drive time to work in minutes. Maybe that's meters. It doesn't really matter. It's sort of nonsense data. But notice, in general, there is a trend here. As a person's weight goes up, the more people weigh, it looks like the less they have to drive to work. Now, if you're trying to look at this in terms of correlation and causality, are these things related? We'll get to that. It's a nonsense relationship. But if you look at the data, there appears to be a correlation between weight and drive time. But in this particular case, it is a negative correlation. As weight gets bigger, as people's weight goes up, the amount of time that they drive, and again, that looks like meters, it could be minutes, the amount of time that they drive goes down. This would be an example of a negative correlation. And I am sure you are wondering, what does no correlation look like? And I've got a tab for that. Here's another data set. I've got people's weight, and I've got their favorite number. Are people's weight and their favorite number correlated? Again, this is made up data, but if you look at the data set over here, there doesn't appear to be a very strong correlation. So unlike when I had a negative correlation and it looked like the trend went down as people's weight went up, unlike the positive correlation where it looked like people's height went up as their weight went up, if I look at people's weight, those same 10 people, and I also ask them their favorite number, when I graph those two things, it doesn't look like this is necessarily going up or going down. I can't really determine a correlation. So this would be an example, just looking at the graph, and we'll get into numerically how to do this. This is an example of a data set that appears to have no correlation between the two variables, in this case, weight and favorite number. So far, what we've done in determining whether a linear relationship exists between two variables, we're putting it on a graph, and we're looking at the graph and we're saying, looks like they're both going up. Hey, that's a positive correlation. Or we put it on a graph or scatter plot, and you go, whoop, looks like we're going down. That's a negative correlation. Or in the third case, well, I can't tell what's going on here, and there's no correlation. And that's not wrong, but what we're going to do next is we're going to look at a correlation coefficient to be able to quantify the relationship between two variables. So it's not just a matter of, yep, looks like that line's headed up, or looks like that line's headed down. We're going to look at correlation coefficients with that same set of data to determine and quantify how good of a relationship do I have between two variables. Here we have our positive correlation. Weight and height are positively correlated. If I were to look at my data set, here's my scatter chart. I'm going to come up with an equation that represents this. This comes up in 4.2. And I'm also going to get a correlation coefficient. So I'm going to walk through how to do that. I've got my data graphed. I select my data in Excel, and then I right click. And then I have these particular options. I'm going to go down to the option of add trend line, ... And I'm going to click that. And I have these particular options. I have different options for different types of trend lines to add. All we're going to be looking at are linear trend lines. So if you see linear there, that's what I'm going to look at. If you say, boy, the world is a boring place, is there not more than just lines? And the answer is yes. You could have polynomials or moving averages. There's lots of other trend lines you could have. We're only doing linear. So I'm going to select a linear trend line, and then I'm going to come down here to the bottom, and I'm going to say display equation on chart. This is used in section 4.2, but I want you to see it now. And I'm also going to click display R squared value on chart. So I get both of those things displayed on chart, and you can kind of see it pop up over here. I'm going to take this and I'm going to move it over here, and I'm going to make the font just a little bit bigger so we can see it better. Okay, so I've made it a little bit prettier. And so what I have displayed on my chart here is I have an R squared value displayed, and I have an equation for the line or the relationship between the dots. And notice that I also have this line that's drawn right there, much better than I did when I tried to draw it. Excel drew this line for me. That's the line that fits this data the best. This value right here, that's your R squared value. And we'll get into this in more specifics, but the closer this value is to 1, the better this line matches the data. If you look at the value here, if you remember back to algebra, the fact that this value right here is positive, it's 0.1418, that positive value tells you that there's a positive correlation between my two variables. I'm going to do the same thing with negative correlation. So if I were to have my negative correlation and I want to display the equation on the chart, I select my data and I right click and I click add trend line. I'm going to select linear, display equation on chart, display R squared on chart. And then I'm going to move this value up here and make it a little bit bigger. There, I made it a little bit prettier so we can see it. So notice in this particular case, I have an R squared value. That's a value that's telling me how good a job this line does matching the data. And notice I have a negative slope on the equation for my line. That means there's a negative correlation. This line here that describes this data is going down. Now let's do it with no correlation. If I look at my data set with no correlation, I'm going to repeat the same process. I'm going to select the data, add trend line. I'm going to display equation on chart, display R squared on chart, and then I'm going to move it around and make it a little prettier. And then I have that equation and that R squared. Notice that the R squared value here is very small. It is close to 0. What that tells me is this line right here doesn't fit this data very good. The closer this R squared value is to 1, the better this line fits the data. So the fact that my R squared value here is low, 0.0003, tells me it's not a very good fit for the data that I have. So if you're looking at this case where there's no correlation, so we're saying, hey, there's no correlation between a person's weight and their favorite number. And part of how I can tell that is because this R squared value is really close to 0. I'm using that R squared value, that square of my linear correlation coefficient, to interpret the relationship between two variables. The closer that value is to 1, the stronger relationship that I have between the two sets of data. So weight and favorite number, they don't seem to correlate very much. If I look at this particular relationship, I've got an R squared value that's 0.7894. Now that's not perfect. If it was a perfect correlation, and we'll get to that in a minute, that would be 1. But, in general, as a person's weight goes up, their drive time is going down. So there is a correlation between those two, and it's pretty strong. It's a negative correlation. And if I were to look at this data set, and I don't know why that's selected, let's unselect it. Again, I've got a higher R squared value that's there. And I've got a positive relationship, a pretty strong relationship between the two. But notice that even with a strong relationship, each one of these points doesn't perfectly line up on the line. In fact, it's a little bit off of the line. And the same thing is true of the line that's here. If I'm looking at this line here that Excel drew and said this is a best fit line, notice that each one of those points, or many of those points, they're away from the line. So it's not a perfect fit. If I were to have a data set that has a perfect fit, and I'll show you an example here and we'll get to this in a little bit. If I have a data set and it has an R squared value of 1, then the data perfectly fits. And if you notice this data set, and I'll describe it here in a minute, all of the points line up on that line that is there. And you might say, where in the world did this line come from? I'll get to it when we talk about causality in just a second. But I want to point out, when you're interpreting your linear correlation coefficient, you're looking, at least for what we've done now, at that R squared value. And that closer that R squared value is to 1, the better or the stronger the relationship is. And that's how you determine whether a linear relationship exists between two variables. Now, the last thing that you see here is explaining the difference between correlation and causality. Things can be correlated, but not necessarily causal. So let's look at our data sets here, and let's look at the positive correlation that we have here between height and weight. So we've got this positive correlation. I've said it's it's positive, it's a pretty strong correlation. But is this causal? Does increasing your weight make your height increase? Does this cause this? So does your weight going up cause you to get taller? Is there a causal relationship between the two? That's the difference between correlation and causality. You could have two things that are correlated, but just because two things are correlated doesn't mean one thing causes the other. An example, again, in this particular case, and looking at this data, if we're looking at our weight and our drive time, um, we might have a relationship here, and these two things seem to be correlated, and they are correlated, in fact. But does how much you weigh determine how long that you drive to work? In this particular case, most likely, unless there's some underlying factor I haven't considered, then your weight and your drive time are correlated, but your weight does not cause your drive time to change. So, what would be an example of something with causality? And I'm just going to give one, and this has a perfect relationship. Every causal relationship isn't going to be perfect like this one. But in this particular example, if we looked at, again, our 10 favorite people right here, if we looked at how much they weighed in pounds, and we compared that to how much they weighed in kilograms, there is a causal relationship between how much a person weighs in pounds and how much a person weighs in kilograms. You might feel better if you're looking at your weight in kilograms, right? So if I'm kind of down here with Jim, we'll just be ambitious and say I'm down here with Jim. I might feel better if I step on the scale and it says 99 instead of 218. But really, I haven't changed what I weigh. There's a one-to-one or a direct correlation and causality between how much I weigh or Jim weighs in pounds and how much I weigh or Jim weighs in kilograms. And in fact, if you were to graph the relationship between weight in pounds and weight in kilograms. I'm failing with my lasso. Just excuse me here while I play with my lasso. There we go. If you look at the relationship between weight in pounds and weight in kilograms, you're going to notice that it falls perfectly on a line. And it's just because weight in kilograms and weight in pounds is just a matter of multiplying by a particular number. The point here is not that conversion so much as to say this and this are causal. Your weight in pounds causes your weight in kilograms to change, and the relationship between the two is a perfect relationship. And you can see that because your R squared value is 1. So to go back and recap what we looked at several examples of scatter diagrams. So we looked at different examples of scatter diagrams. We calculated a linear correlation coefficient. In this example with Excel, we used R squared. We're going to look at R as we look through the PowerPoints, but that R squared value is what we use in order to determine whether or not I have a linear relationship between two variables. One way to determine if I have a linear relationship is to graph it. And if it's kind of in a line, then I've got a linear relationship. But I can also use this R squared value to tell how strong that relationship is. And then the last thing is just because two things are correlated does not mean one necessarily causes the other. And I'll sort of end with one of my well, I'll give a couple of my favorite examples. So this is from a website of spurious correlations. And this is comparing the number of people who die by becoming tangled in their bed sheets compared to the per capita consumption of cheese in the United States. And so you look at those two things, and again, this one's not linear, but you see this and you say, wow, those two things must be related. They must be correlated. And in fact, best I can tell, they're correlated, but they're not causal. Eating more cheese doesn't cause death by bed sheet. And here's another silly example. And I don't know why other examples have to do with people dying. I didn't make up these examples. But if you compare the number of people who drown by falling into a swimming pool, that correlates with the number of films that Nicolas Cage appeared in, or at least so says this data. So we might say that this data is correlated, again, not linear, but not causal. Nicolas Cage being in a movie doesn't cause one to fall into a swimming pool, or vice versa. So going back to our last point here, we can have correlation. Two things can exhibit a particular trend, but one doesn't have to cause the other. And we'll look at some of the nuances of how you distinguish between correlation and causality. But if you've got a high R squared value, you're going to have correlation. Hey, these two things can be correlated. I can determine that with my R squared value. Determining whether it causes it, that's a separate question.